Hello, this is lesson 02. In this lesson, we will learn about the components of the Uno board, as well as C programming in Arduino, including how to declare and instantiate variables and operations between these variables. We will also talk about some advanced math functions and getting random numbers. We might not be able to get to this today because the course might take this lesson might take a long time. First, let's introduce the Uno board. Introduction. Alright. Like this. 2. And then the Uno board has 4 LEDs. Let's get a picture of the Arduino Uno board. Go to images. Let's do this one. Nice and simple. Alright. Has 4 LEDs. So the first one is this on button right here. Okay, this is quite big. The on light shows that the board is being powered. So if it's plugged in to a USB-B or a power jack. The L light is an LED that we can control with our code. The L LED is this one here. Next, the TX light shows that data is being transmitted. So data is being transferred from the IDE to the board. And then to show that it's being received, the RX light shows that data is being received. Now, pins. Let's talk about the pins on the board. So, let's give this LED 3, and then pins. There are digital pins. The digital pins can either be high voltage or low voltage. And analog pins can be a whole range of values from 0 to 5 volts. 5 volts. And then from these pins we can connect breadboards to create circuits with electrical components like wires, resistors, LEDs, potentiometers, and so much more. Alright, now what differentiates the digital pins from the analog pins is that digital pins can only be high or low, and analog pins can be a whole range from 0 to 5, but they are divided into 1024 different sections because that's how many bits. Alright, now let's look at the Uno board under the microscope. Okay, so this is the Eligu Uno R3 board under a microscope. And then we can see here, this is the on LED I was talking about. This is right here, on LED. And then to the left, we have the L LED. The L LED is this right here. And then TX is here, and RX is here. So this is the transmitter LED, and this is the receiver LED that shows when data has successfully been transmitted and received. Here, this is a chip that allows the ports to be connected successfully and the drivers. This is a crystal oscillator, and then these two are capacitors, 47 microfarads and 25 volts, and then power can be supplied through the USB-B port, which is this big chunk right here, or a power jack here. And then lastly, there's the CPU, which let's flip it around. The CPU, which is Atmel, Atmel's ATmega 328P. So yeah, this is the Uno R3 board. Let's flip it over. Yeah, so there's the big Elugu logo on the back as well. This one here gives out 3.3 volts of battery, or 3.3 volts of voltage. This is 5 volts, and these two are the negative ends, the ground. And then over here, these are analog pins. So there's 6 in total, 0, 0 to 5, and then these can accurately measure the sensor's voltage. Goes from 0 to 5 with 1024 different settings. And then over here, these are let's flip it over. These are the digital pins. So it goes from 13 to 0, so there's 14 in total. And the ones with the squiggly lines in front of it, like 3, 5, and 6, those are PWM. And then at the very left, there's a ground. And that is the showcase of Elugu's Uno R3 board. Back to the video. Next, let's talk about declaring instantiating variables. So this is heading 2. Oh wait, no, this is heading 1, sorry. And to write any code, the most basic aspect are variables. Let's learn about declaring and instantiating variables. The format for declaring variables is data type and variable name. Let's give this a new line. And then example is integer and then year. This means that this word year now becomes an integer. Let's highlight this, turn this red, and then we can turn this back to black. So now we can write integer here and then say year is 2024. Now this means we declared the variable and then we gave it a value. So now whenever a year comes out later, the board will know that it is 2024. Next, we can put these together simultaneously. And to do that, we can simply write example integer year equals 2024. Don't forget the semicolon. Alright, let's test this out in the Arduino IDE. Alright, so we can declare the variable integer year, and then year equals 2024. Okay, let's set it up. Let's put it into the serial manager, which is serial.setup. Oh, not begin, I think. Let's say 9600, and then serial dot, let's print a few lines at the top. And then let's print year equals, and let's print the year. Okay, now let's, oh, I forgot the semicolons, sorry. Oh, another one. Oh, I forgot to select the board. Like this. Now it should work. Alright, now let's upload it onto our board. Let's open our serial manager and see the year is 2024. Okay, so now we know how to set variables. Let's talk about the types of variables. I think these are supposed to be heading 2 actually. Heading 2s. Alright, so types of variables. Let's make a table so it's easier to see. Okay. Let's give it 3. Okay, so we're gonna go through the data type. We're gonna go through the size, which is in bytes. And then we're gonna go through the value range. So the first one is called a boolean. A boolean has a size of 1 byte, and the range is a logic true or false. So if we want to set one in here, we write boolean, and then let's say just x instead of year, easier to, and then let's say equals true. Now let's print this. Okay, let's upload it. So now x equals 1. So 1 equals true and 0 equals false. Alright, now we know the booleans. Insert new row. Let's talk about char, which is character. This is also 1 byte, and the value range is from -128 to +127. So let's turn this into character. And the reason characters are numbered is because this follows the ASCII chart. We can ASCII chart, which is this kind of complicated chart of some of these like symbols and letters. And let's say 65, which should be capital letter A, I believe. Yes, so this is A. So if 65 is A, then 66 must be B. Yeah, so this is B. Alright, then anywhere from negative 128 to 127 is a unique character. After characters, there are bytes. One byte, the byte data type has one byte to it. And then the value range is from 0 to 255. And so it can store a number, let's say 30. If we run this, then the output would be 30. Now you must be wondering, why is there a limit to it, 255? And 0 to 255, there's 256 in total. So if we do something bigger than 255, let's do 256. Then you see it won't say it's wrong, but it'll just say this is 0. And how does that work? It's because, let's pull up a paint. And that's because 1 byte is 8 bits. 1, 2, 3, 4, 5, 6, 7, and 8 bits. And they can either be 0 or 1. And then this is in binary, and so this, if there's a 1 here, then it would be 1 in decimals as well. But right now, let's delete these. If we make all of these 1, then added together, this would equal 256. And from 0 to 255, there are exactly 256 in total. Now, if we make it 1 more, then it will become 1, 0, 0, 0, 0, 0, 0, 0, 0. And since the computer only looks at this section, it will think that the number we had is 0. And that's why it outputs a 0. If we make it 1 bigger, 257, then on this right here would be a 1. So even though there's a 1 here, the computer thinks the whole thing is only 1. Let's test this out. 257. Yeah, so now it's 1. So now we want to have numbers bigger than 255. So naturally, there will become an integer. Now the integer is 2 bytes, and the value range increases drastically. It goes from 256 values to 64K. So negative 32,768 to 32,767. So added together, there's 64K. And that's because this is 2 bytes, so 16 digits. And then we can turn this into integer, and then this is, we can write a bigger number, let's say 30,000. Now this would be 30,000. Now let's write something a little bigger. Let's say 32768. This is over the value range. Let's see what happens. Okay, now what happens here is that suddenly this number becomes negative. This is because out of the, okay, let's delete this first. Out of the 16 digits, so if this is two bytes, and we divide these into 8s, like so, then this last digit right here is used to determine whether the value is positive or negative. So if this is a 0, it means it's positive, and if it's a 1, then it means it's negative. So there's 15 digits in total that is used to represent numbers. So, and since each one can either be a 1 or 0, then it would be 2 to the 15th power possibilities, which would be, which is 2 to the power of 10 multiplied by 2 to the power of 5. And since 2 to the power of 10 is roughly 1000, then this would be 32k. And then, since this number exceeded 32k, then there is a 1 here now in the 16th one, and it confuses the code to think that this is a negative. So it becomes negative 32k, and that's why there's a negative sign here. So that is integers. Be careful that there's a negative sign. Alright, after integers, there's a word. So a word is basically like an integer, except it does not have negative numbers. It goes from 0 to 65535. So instead of going from a negative to a positive, it goes from 0 to a positive. You can store bigger numbers in here. You can go 60,000. It'll be fine. Make sure to change this into Word. Now this is 60,000. That's remarkable. And after Word, there's a long. Now this is just 4 bits of data. This goes from negative 2,147,483,648 all the way to positive 2,147,483,647. How do we pronounce that? That's 2,147,483,648. That's quite a lot. 4 bits. And so we can write a really big number in here. Say 2 billion. Like that. Change this to long. big numbers. Okay, after long, there is a float. Now, you might have noticed that for these, we could only give whole numbers. If we wanted to give decimal points, we would have to use float. This uses 4 bytes, and it's from negative 3.4028235e plus 38 to 3.4028235e plus 38. For those that don't know, e means 10 to the power of, and then the number afterwards. So this is 10 to the power of 38. And then the float, so that means if we change this to float, we can add a decimal point in here, and then, for example, 2.4. And that's the output. Sorry, 2.4. And then how the value range was determined is quite complicated. I'm not gonna go over it in this lesson. And then after float, there's a double, also 4, in the same value range. This is pretty similar to float, so I won't go over it. Okay, now let me just reiterate the things I talked about for the whole bits and everything. So the size determines the value range for each data type. A byte is 8 digits of binary numbers, so 8, 0, or 1s. Since each digit has the possibility of 2 distinct values, an 8-digit byte would have 2 to the power of 8 different possibilities. That's 256. Using this same method, we can derive the value range of integers and words, which are 2 bytes, and long data types, which are 4 bytes. When dealing with float and double, these are very complicated, so I won't go into detail here. Okay, and so that's what we talked about in the paint masterpiece that I drew. Next, let's talk about local and global variables. These variables can either be local variables or global variables. Local variables are inside a function and only appear inside that function block. Global variables, on the other hand, can be used everywhere or anywhere, but must be set at the start of the sketch. So for example, our float right here, 2.4, right here, we have this in the setup. We have the print function and the float all in the setup. But if we wanted to, we can move the print serial.println x into the void loop, and let's see if this works. So we can see there was an error because x was not declared in the scope. This can be fixed if we move the float outside to make it become a global variable. This way, the float should be able to print. or we forgot the semicolon. So now it should be able to print. Oh, now it's printing in a loop. So there's a lot being printed. Alright, let's move this back in here. And then use this one again. Go on to the next example. Stop the loop. Alright, now we have talked about global and local variables. Let's go on to math operators. Math operators are really important for programming too. Let's go heading 2. So again, another table like this. Insert table. So this, we can talk about the operator and then how it works. So let's start with some simple ones. Plus or addition. So if let's turn this into an integer, x equals 2, and then y equals 1, we can do integer z equals x plus y. Now x plus y, we all know 1 plus 2 is 3, so z, so let's see, semicolon, can't forget those. So yeah, 2 plus 1 is 3. Now, when we talk about addition, of course, we will talk about subtraction as well. Subtraction. Now, 2 minus 1, that should be 1, right? 2 minus 1. So, z equals 1. Now, after addition and subtraction, naturally there is multiplication. Multiplication. So, okay, 1 plus 2, 1 multiplied by 2 isn't interesting. Let's do this. 20 times 10. Now that should be 200. Let's see. Alright, 200. After multiplication comes division. Division is 20 divided by 10. This should be 2. So yeah, this is 2. Now if we change this number up a little, let's do 20 divided by 15. How much do you guys think this would be? So 20 divided by 15. Go into the decimals, right? But we can't forget that this is an integer, so this would become 1. It makes all of the remainders go away. This is something you have to consider when coding. To find the remainder, you can use another operator called modulus. Make this capital, modulus. Okay, and then let's do 20 divided by 15 modulus. This should be 5. So 20 divided by 15, there is a remainder of 5. After modulus, we can talk about some other things. For example, increment. This is not multiplication. This is something else. Increment. So let's say x is 20, and then let's do x plus plus. This means increment, and or let's do integer z, and then say z equals this, and then so increment means whatever variable plus 1. So 20 plus 1 would be okay, let's do this, and then integer z equals x. Oh, alright, let's just get rid of the z and put x here, like this, to make it simpler. So do 20 and then x plus plus. Like this, it should be 21. Let's see. So now it's 21. So when there's increment, there's decrement. So it's minus, 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 which is decrement. So x minus minus. So 20 minus 1, that should be 19. Let's see. Yes, so that's 19. And after these, there is not and or. These are really important as well. Not is a simple exclamation mark, logical not. So these are for booleans. Let's say x is true and y is false. Don't forget to change the variable type to boolean. Everything boolean, and then if let's say z is not x, so since x is true, then z should be so right now print line is x, my bad. Let's turn this to z, and then so x is true, then z should be false. Yes, so again, 0 means false and 1 is true. So this is not. And then and is logical, and is two and signs like this, which means logical and. So this, how this works is, let's say x and y. If both of them are true, then this returns a true, otherwise it will return false. So since one of these is false, it will return false. This, so now it's false. And then if we turn both of these into true, then it will be true. So now it's true. After logical and, we have logical or. So this is like this, logical or. So this means if there is one true, no matter how, if there's one true in here, then it will return true. Otherwise, it will return false. So let's change one up. Like this, if there's one true, then it will return true. And if both of them are false, then it should return false. Yep, so now it's false. After logical and, not and or, there is a bitwise and an or. So bitwise, there's only one as opposed to the two. So one and sign means bitwise and. So bitwise and, let's do bitwise. We no longer have to use booleans, we can use integers. Integers, let's do 30 and 5. Good numbers. And right now we're doing bitwise and. Alright. So let's see. 30 and 5. And surprisingly, this equals 4. Now let me explain how this works. So let's get out the handy paint. Okay. Now we're using 30. So let's open a calculator. Ooh, quite big. So 30 is 0, 0, 0, 1, 1, 1, 1, 0. So 0, 0, 0, 1, 1, 1, 1, 0. And then 5 is 0, 1, 0, 1. And then you can add in the extra zeros. This is an and sign. So this is 30, and then this is 5. So how bitwise and works is that we compare every single digit. So the ones, the tens, or we can't call it that because this is binary. Alright, and then 0 and 1 together. So since it's and, it's 0, 1 and 0 is 0, 1 and 1 is 1, 1 and 0 is 0, and 0. So let's see, 100 in binary is 4. So, and then this is how 4 got here. Now, after bitwise and, we can have another one called bitwise or, which is only one vertical line instead of two. This is bitwise or, and then we can change this up here, and then let's run it. So it's 31. Let's see how that works. Let's erase this part, and then let's calculate. So since this is or, this is a 1, this is a 1, this is a 1, this is a 1, and this is a 1. So 1, 1, 1, 1, 1, 5 ones, which should be 1, 1, 1, 1, 1. This is 31, yeah. That's how we use bitwise or. After all the not and ors, both logical and bitwise, we have shifting. So there's left shift. So we can left shift once, so X, left shift Y once. And this is 60. So let's see how that works. So we start off with 30, which is 1, 1, 1, 1, 0, 0, 0, 0, 0, 1, 1, 1, 1, 0. So, okay, instead of integers, let's instead use bytes, because that would work a lot better and is simpler to understand. So, oh, it's still 60, alright. So this is 8 bits, and we moved it to the left once. So let's draw a bad line. If this is a line, and then let's draw a tick at every single part where there's a digit, and then let's move the whole thing left 1, so like this. And then now we can see there's a digit with nothing in it. If we ever find any of these, then we put a 0 there. So, and then let's put this through our calculator. 1 1, or shoot, here 1 1 1 1 0 0. So 1 1 1 1 0 0. So yes, that's 60. Now let's shift it a little more. Let's go 5. So if we do 5, it will go to 192. How that works is that let's go back like this. This is 30, and then we shifted to the left 5 times. So 1, 2, 3, 4, 5. So only these 2 ones remained, and everything else is outside of the byte, so the computer no longer looks at it. So this is 1 1 0 0 0 0 0 0. So 2 ones, 2 ones, and 6 zeros. And that's 192. Now 192, this is left shift, and then let's do right shift. So this way, right shift. So let's see, let's do 1 first to make it simple. So it's 15. So instead of this going to the right, and now, or instead of going to the left, now it goes to the right one. And we started with 30. How much was 30 again? Let's see. 4 ones and a 0. So let's erase this for now. Let's go 4 ones and 1 0. Alright. 0, 1, 1, 1, 1. The rest is zeros. And then let's move all of this right 1. And then since there's one that's no longer here, we put a 0 in here, and that is just 1 1 1 1. So 1 1 1 1 is 15, like so. So theoretically, no matter how big the number is, if we just move right shift enough, then it will become 0, like this. If we right shift 100, then it will be 0. So for today's homework, today's homework, it is to take a picture of the words on the CPU with a phone. And a bonus question, find the answer to 36 modulus 7. So again, modulus is the percentage. It's finding the remainder of 36 divided by 7. Alright, that should cover lesson 2 of the Arduino and C series. Thank you for watching.